As developers, all we do is practically manipulate state and display it in a structured way in user interfaces. In distributed systems that are composed of multiple applications running over the web, the state must be transferred between multiple applications in order to satisfy the functionality of the system. This is achieved by using communication protocols that allow for the manipulation of state in distributed scenarios. One such protocol is REST. REST stands for Representational State Transfer and is an architectural style, or a protocol if you will, developed on top of HTTP that dictates the contract that an API should expose for manipulating the state throughout the World Wide Web. From an architectural standpoint, a RESTful service is usually described by the following 6 architectural constraints. Client-server architecture. This means that communication with the REST service is done in a request-response fashion. Client sends a request, server processes it, and returns a response. Statelessness. REST services do not hold any session state for identifying the client between subsequent requests. As such, the client does all the work in providing his own session state, via a JWT for example. Uniform interface. The uniform interface practically specifies that the REST service should expose a clear contract which the client can use in order to obtain and manipulate state. Cacheability. State can be cached in order to improve overall performance of exhaustive operations done on the service side. Layered system. A RESTful system's components can be abstracted away by proxies or load balancers without the client having to know this detail. Code on demand. A RESTful server can give clients precompiled code that the client can use directly. Although it is a constraint, in practice nowadays it's not so often used. At a conceptual level, a RESTful service stores state in the form of resources. Each resource is identified throughout a RESTful API by an URI. The client can obtain a specific representation of that resource via content negotiation done at the level of metadata. For filtering resource representations, the client has the option of using query parameters. The server can inform the client with regards to the status of his request via status codes. These status codes are grouped into different categories. For example, 100 info, 200 success, 300 redirect, 400 client error, 500 server error. Representations of a specific resource can be obtained or manipulated by the client by using HTTP verbs. Options ask the API to see what operations are available, get, retrieves that resource, posts, creates a resource, put, updates a resource, patch, partially updates a resource, delete, deletes a resource. Simple. Let's have, for example, a resource that exposes a set of users which is located at a specific URL. If we make a call using the options method, the server will tell us exactly what operations can be performed on that specific URL, coming from what origin and also what caching policies are in place. If we execute a GET call on the resource, we should obtain a representation of a list of users. By using query params, we can filter the representations based on our needs. We can identify a specific resource by using its unique identifier. As the server allows us to negotiate our content, we can ask for a different representation of the resource via metadata, transmitted in the form of HTTP headers. Also, if we just need some specific properties of the resource, we can let the server know this by using the field's query param. If we want to create a resource, we can use the post HTTP verb having the resources representations in the body. Once created, the server will let us know that the resource was successfully created and will give us its location as part of the return metadata. We can partially update the resource's representation via the patch verb. If we want to change the resource totally, we can do this via the put verb. If we want to make sure that no lost updates occur, we can make use of e-tags as to ensure that no update is lost. For deleting a resource, we just have to use the delete verb. Richardson maturity model. Because REST is very permissive, the Richardson maturity model allows you to evaluate the maturity of a REST service on 4 distinct maturity levels. Level 0, POX. Level 0, or plain old XML, denotes a messy implementation of REST where endpoint and operation information is specified as part of an XML payload without using any of the beneficial recommendations of REST. Level 1, resources. Level 1 suggests that we separate the endpoints for manipulating state based on resources. A resource will represent a collection of state objects that can be manipulated according to a contract. Level 2, HTTP verbs. Level 2 implies using HTTP verbs in order to manipulate the state of resources. Instead of using just get and post methods, in combination with a messy URL scheme, HTTP verbs allow for the definition of individual operations at resource level, thus exposing a far cleaner contract. Level 3, HateOS. HateOS suggests that the REST service should offer meta information about the resource so that the client knows exactly what operations can be performed and how to perform them. As such, clients will always be happier when using Level 3 RESTful systems. As REST is very versatile, each development team should define their own way of working with REST from a maturity and style standpoint.